I'm Donna Nelson from the University of Oklahoma, and this is a lecture for my organic chemistry class. This is the third lecture from Chapter 18, Aromatic Substitution Reactions, and the PowerPoints were created to match David Klein's textbook in organic chemistry, as all of them have been. So let's look at what is in this third lecture. You're here, this is the first lecture, second lecture, third lecture. So we're looking at the activating and deactivating effects of substituents, and also the directing effects of those substituents, which are already on the ring when a second or subsequent substituent is added to that ring. So let's look. So what we've seen so far is we have seen activating groups and deactivating groups, and except for the halogens, these groups all follow one pattern. An activating group is ortho-para-directing, and a deactivating group is meta-directing. Now, what is meant by activating is it means rate increasing. Deactivating means that this substituent causes the reaction to occur at a slower rate than if it were not present. So activating means rate enhancing, deactivating means rate retarding. The activating groups are all ortho-para, deactivating are meta-directing. So halogens are different. Halogens are actually deactivating and yet ortho-para directing. So halogens are sort of in between here, and we will look in detail at that. Halogens withdraw electron density by induction, and so they are deactivating, and induction means through the sigma bond, yet they donate electron density into the ring through resonance, and that means through overlap with the pi system, and so that makes them ortho-para directing. So here you can see the electron withdrawal through the carbon-chlorine bond, using chlorine as an example. And so this causes the ring to be, this causes the molecule to be deficient in electron density, and that's in the sigma system, but the sigma system will cause the pi electrons to be held more tightly, and that will cause the rate to reduce. Yet, the halogens also donate electrons through resonance, as you can see here in depicted by these resonance structures. And so you can see chlorine donate a pair of electrons into the pi system, and you can see the carbon-chlorine double bond here, and the negative charge is in this resonance structure. It's at the ortho position, now it's at the para position, now it's at the ortho position again. And so we are back to the resonance structure with chlorine being neutral, yet you see that the electrons have migrated around the ring. So there are indeed 5 different resonance structures for this molecule. So, if chlorobenzene reacts with the nitrosonium ion, you can see the pair of electrons in the ring is donated, does an attack on nitrogen at N+, and that generates a positive charge here at the carbon next, the carbon that is bearing chlorine. This is attacked at the ortho position, and you can see that this carbon at the ortho position now is bonded to 4 different atoms. So this is the sigma complex. And so now you have the positive charge borne by the carbon, which bears chlorine. The positive charge can migrate through the ring. And now you have this resonance structure in which chlorine can donate a pair of electron density in to satisfy that positive charge. And now the positive charge is residing on chlorine. The same types of resonance structures can be drawn if you have attack at the para position. And so now, once again, that you can draw a resonance structure where the carbon bearing the chlorine substituent is bearing a positive charge also, and the pair of electrons on chlorine can come in and satisfy that positive charge. That makes chlorine bearing a positive charge. And so you have this fourth resonance structure if you have ortho attack or para attack. But if you have attack at the meta position, you cannot draw a resonance structure in which the carbon-bearing chlorine also bears a positive charge. And so this fourth resonance structure cannot be attained. And that makes the attack at the meta position less favorable. Attack at the ortho or the para position has a lower energy barrier to achieve that sigma complex because the sigma complex is more stable. It has a fourth resonance structure. The attack at the meta position gives rise to a sigma complex that does not have a fourth resonance structure. So this is less stable. It will be higher in energy, and the transition state, the energy barrier leading to this sigma complex will be higher in energy. So this reaction occurs much more slowly if it occurs at all. Now let's review the reactions that you've seen. You've seen strong activators with ortho-para directing effects. And here we have noticed that these all have pairs of non-bonding electrons, non-bonding electrons, non-bonding electron, non-bonding, non-bonding. And so these are all easy to remember. Now, these are all strong activators. This one actually fits this pattern up here, but instead of just having one substituent, this one has two substituents. So in some cases, although this book characterizes this molecule as a moderate activator, I have seen this also categorized as a strong activator, and I actually prefer to put it up here along with the strong activators because that makes it easier to remember this group. This group is going to be, is always going to have non-bonding electrons, a non-bonding pair, a non-bonding pair, non-bonding pair, a non-bonding pair, such that it can activate that ring by donating electron density into the pi system. Now let's look at these moderate activators here. They still have ortho-para directing effects. Notice they also have pairs of electrons, a pair of electrons, a pair of electrons. But these electrons are also in conjugation with this carbonyl. And so these electrons are not so free to interact with the pi electrons in the benzene ring. And so that makes these functional groups less activating because the electrons are tied up with the carbonyl. They are in conjugation with the carbonyl. So up here, the strong activators have non-bonding pairs, which are not in conjugation with the carbonyl. So that is the difference between these two classes. Then also you have the weak activators. These are just alkyl groups. They donate electron density into the ring, and so they do make the reaction the electrophilic aromatic substitution reaction go a little bit faster, and they are ortho-para directing, but weakly. So all of these substituents are activating groups and ortho-para directing. Now let's look at the deactivators. So let's group these. Nitro, an ammonium group, and a carbon that is bearing electron withdrawing groups. So these are strong deactivators. That means that they will reduce the rate of the reaction greatly, by 100,000 or a factor of 100,000 perhaps. And let's look at what they have in common. Here, this nitro group, if you draw this nitro group out, you'll see that the nitrogen is bearing a positive charge. And here, this nitrogen is bearing a positive charge. And here, this carbon is going to be bearing a significant positive charge, but not so strong as here. But nevertheless, it's bearing a sufficient positive charge so that it, because it is directly attached to the benzene ring, it will withdraw electron density greatly. And so these are all strong deactivators. And you have seen us go through the resonance structures and the sigma complexes, so that we have already discussed how these will be meta-directing, and also the moderate deactivators are meta-directing. So we saw that in the last lecture. So you have that. You can pull that up and watch that again if you need to. Now let's look at these, the difference in this group versus this group. Here this is bearing a full positive charge and a large partial positive charge. Now what we have is we have groups that have pi bonds. You can see groups that have pi bonds. The carbonyl is polarized so that the oxygen is bearing a significant partial positive. The carbon is bearing a significant partial positive. That carbon with a significant partial positive being directly attached to the benzene ring pulls electron density out of the ring and deactivates the ring towards the reaction. And it's the same way here. You can see that this sulfur-oxygen bond is going to be polarized. Oxygen will bear a partial negative. Sulfur will bear a partial positive. Similarly here, nitrogen will bear a partial negative. Carbon will bear a partial positive. And anytime that you have that atom, which is bearing a significant partial positive charge directly attached to the ring, it will reduce the rate of reaction and direct the substitution to the meta position. Now, weak deactivators and ortho-para directing. This is the group that is the exception. Okay, all of this and plus what was on the previous slide is summarized in table 18.1 in your book. This essentially is the bottom half of that table. And we have discussed how the halogens will withdraw electron density through the sigma bond from the sigma system. It withdraws electron density from the sigma system, which makes all of the electron density to be held more tightly closer to the nucleus. That reduces the rate of reaction. So the halogens are all deactivators, and yet, since they have the non-bonding electrons, which can be donated into the ring, just like these, these will be ortho-para directing, and yet they will be weak deactivators because they withdraw so much electron density through the sigma system. Now, sometimes you'll want to do multiple substitutions. So let's look at this case in which you have nitrotoluene. So nitrotoluene. Nitro is a meta-director, as you just saw. The alkyl group is an ortho-para director. In this case, the directing effects of the substituents reinforce each other. So the methyl will direct the incoming substituent to the ortho positions, not para, because the para is already occupied. The nitro will direct the incoming substituent to the meta position. And so these two are reinforcing each other. The directing effects are reinforcing each other to put the incoming substituent on the same carbon atom. Now, what if the directing effects of the substituents, the existing substituents, oppose each other? So here, the hydroxyl group is ortho-para directing. You ignore the para because it's already occupied that position. And so the hydroxyl will have a tendency to put the incoming group, whatever it is, the incoming group will go ortho to it. Now you have the methyl group, which will direct the incoming group, whatever it is. It could be nitro, it could be something else. Whatever the incoming group is, the methyl will direct that incoming group to positions ortho or para to it. The para position is already occupied. So each of these is directing the incoming group to go ortho to it. And so you have to consider which one is the stronger ortho-para director. And here between hydroxyl and methyl, hydroxyl is the stronger ortho-para director. So it wins. So the incoming group, whatever it is, goes ortho to hydroxyl. In some cases, if there's a significant steric effects, like this group, this isopropyl group, is going to have significant steric effects. And so whatever the group is that's coming in, this is the incoming group is going to be ortho-para, directed to the ortho and para positions. But because of the steric effects of this isopropyl group, the incoming substituent will go mainly to the para position, because steric effects will make this the minor isomer. For 1,4-disubstituted ring, substitution will occur at the less sterically hindered site if more than one site is favored by directing effects. So here, this is favoring ortho-para. The para is blocked. And this methyl group is favoring ortho-para, but the para is blocked. So here, the major isomer is that one that is due to the ortho directing effects of this methyl. So the nitro, or the incoming group, whatever it is, went ortho to the methyl group because of the steric effects up here. Now, we have this example of 1,3-disubstitution. And so whatever the incoming group is, it could be nitro, it could be anything else. You can see you've got two groups adjacent to this position. And so this position is going to be sterically blocked. You will not observe nitration at that position in between these two substituents. And so you have to just consider you're going to have ortho-para substitution due to this group and ortho-para substitution due to that group. And so this is the ortho and para position. Notice that you have no substitution here because that's meta to both of the groups. How could we force a substituent to add ortho instead of para? So this is ortho-para directing. So how do we get only the ortho substitution when you have this ortho-para director in the reactant? So what we do is we install a blocking group in the para position. And then you do the bromination, which will then just be at the ortho position, and then you remove the blocking group. And then you have just para substitution. So you don't have, then you have just ortho substitution. You don't have any para substitution because it was blocked when the bromination took place. So sulfonation, remember, that's the reaction that can be reversed. And so here, one of the carbon-hydrogen bonds will be replaced by a sulfonyl group. And so the synthesis can be accomplished like this. So remember, you can put the sulfonyl on and then you can remove it. And so now you sulfonate and attach the blocking group. Then you brominate. The bromine is forced to go only at the ortho position. It can't go para because the para position is blocked. And then you remove the blocking group with just dilute sulfuric acid. And so that we have now covered the remaining electrophilic aromatic substitution, and we will go on in the next lecture. We will go on to some other reactions of aromatic compounds.